Hello, this is Chris Barton, and I'm going to start us off with our milestone update for week 6 for uplift modeling. So in the last few weeks, we've been working on various uplift modeling approaches. During this presentation, we'll focus on the two-model approach. But before I get into the actual modeling approaches and some of our initial results, I'd first like to go over evaluation of uplift models. So moving forward to the next slide. In this slide, I kind of have some text descriptions about uplift modeling and how to evaluate it and what makes it difficult. So the main reason that uplift modeling is difficult is because it's different than supervised learning in that we don't have the ground truth. So for example, in a supervised learning problem, we might be learning to classify an image. And then your model will predict a classification for an image, and then it'll have the ground truth to be able to say, is this the actual image? Was our prediction right? And then it'll therefore update its parameters to move slightly closer to the real solution. However, in uplift modeling, we can't really do that because, going back a second, the goal of uplift modeling is to figure out, the increase in probability of a purchase given that we show somebody an ad. So that's kind of a complicated definition, but and if we think about our data set, we have historical data from an A/B test. So basically, for all of that historical data, we only have the factual outcome for one of the actions. So for example, we'll have in our data frame, we'll have all of the covariates, we'll have if they're in the test group or the treatment group, and then we'll have, did they get an ad or did they not get an ad, corresponding to if they're in the test or treatment. But that makes it difficult to directly measure uplift because for each individual, we cannot simultaneously show them an ad and not show them an ad. So it makes it quite difficult to actually model uplift and also evaluate it. And traditional metrics such as RMSE and accuracy don't make a ton of sense. There are a couple of solutions to kind of work around this, which I'll kind of talk through here in a bit. So the first solution and kind of the main solution is kind of like a generalization of the traditional cumulative gains chart. But however, instead of looking at each individual person, what we do is segment the population. So to think about this a little bit more and hopefully explain it, what we do is we have our uplift model, and it can, it will give us a score for every individual that basically tells us, basically the increase in probability that they will purchase given that they are shown an ad. So once we have that for every single individual, we can then sort, our data frame by that score in descending order, and we can maybe break this data frame into deciles. And in each decile, we'll have, a handful of people in the test group and a handful of people in the control group. So then with, the people in the test and the people in the control, we can then look at their response rates per decile and come up with a pretty, accurate representation of, how well our uplift model is performing. In the first decile, for example, we would hopefully see the biggest amount of uplift, so hopefully everybody in our first decile, everybody in the control group did not purchase because they did not get an ad, and everybody in the treatment group within the first decile will hopefully, purchase because they did get an ad. You can kind of see this here. This would look like an all right model in the sense that it is descending. However, ideally, say this black box or the black bar was the treatment and the white is the control. Hopefully there would be a huge gap between these two, and say this is one decile. And hopefully this would continue to descend. The gap would probably level off in reality, and then at the very bottom, the very end, you would most likely see people who what we call quote unquote sleeping dogs, which they will purchase if they do not get an ad, but if they get an ad, they will not purchase. So your ad would actually have a negative effect on them. These people would be considered, negative uplift or downdrift. And hopefully the last decile, which remember the deciles are sorted by this uplift score. So hopefully this captures these people here. So hopefully that did a good idea of explaining, the basic idea between or how we measure an uplift model. And again, as I mentioned, this is a kind of a generalization of the Gini metric. and it's called actually the Kidney curve. I believe I'm pronouncing that right. I haven't actually heard anybody pronounce it, so just FYI on that. So here we can see in the right-hand corner what an actual chart like this might look like. So to walk through this, so again, we're kind of segmenting the data, but in this case, we're sorting the data by the uplift score. And then for each percentage of the data, so at 1% of the data, we can look at how our model performs, how actually a random model will perform, which is this diagonal line, and then how like the theoretical max of the perfect model would perform. And then this purple line is how a model with no negative effects would perform. So this way we can see like each percentage of our data. So we can say like at the top 20% our uplift scores, we can see how better our model is doing than a random model versus a perfect model. And you can see this at every fraction of our data set. So this curve offers a pretty intuitive view into how well our model is performing and how it compares to a random and a perfect model. And this kind of offers it's also a good connection between a standard cumulative gains chart, which most marketers are familiar with. Okay, so hopefully this kind of gives you a good intuition of how the evaluation of an uplift model is performed. So moving forward, I can go ahead and get into the actual modeling approaches. So the first method to model uplift modeling is known as the two-model approach. And this is basically the simplest approach there is. And is basically what you do in the two-model approach, as it sounds like, is you develop two models. In the first model, what you do is you subset your training data into the test group and the control group. And you build a model for each group to predict the likelihood of a purchase, given an ad in the test group and not given an ad in the control group. Once you train these models and do your hyperparameter tuning, you can then take these two models and take them to the test set and then score every single person within the test set, regardless of what treatment group they were in, and then subtract the test model minus the control model. And this theoretically gives you the uplift, kind of the increase of probability of purchase given that you're showing somebody an ad. And these models again are kind of like the simplest models you can kind of take basically. There are some drawbacks, which I think we'll probably get a lot more into the drawbacks and kind of the intricacies of it in the final report. But this is definitely if you guys ever do uplift modeling, this is a great place to start. And often actually two model approaches are kind of often used kind of as a baseline versus to compare other models against. You have the random classifier, which is completely like a random baseline. Then you have the two model, which you should be able to hopefully beat a two model with a more advanced model. So in the following slides, we all kind of developed our own version of the two model approach, and we just wanted to see how different classifiers performed with this. So I went ahead and took the first one and built an XGBoost model. So again, I followed the standard protocol by breaking the data set into test and control. I performed a randomized grid hyperparameter search, and then I scored everybody in the test data set and came up with the following graph. So it's very interesting. You can see that the perfect model, almost everybody who responded to an ad can get captured very quickly within the data, and then it goes straight basically until the very end of the data, until 100% of the data set, which is where you have the kind of the sleeping dog, so to speak. The purple line represents if there were no negative effects. You could then go up here and then go straight to the end, and then there's no kind of drop off at the end because there's no negative effects in this model. You have the random model, which is just the diagonal gray line here, and then you have the model that was the two model approach that I did with XGBoost, and you can see it does pretty well, I think. We haven't looked at other models, but just kind of I don't think this looks horrible. It's not like a very thin margin here. At the very end, you can see it does perform worse than actually a randomized model. It'd be interesting to think about a little bit more about why that might be performing worse. It also goes flat here, which a lot of people probably are indifferent to seeing an ad. So I think the model captures that as well. So, and we do see a big spike at the beginning. So we are capturing, in the first decile, a lot of people who did respond to the ad. So overall, I think, it's definitely a good first stab at this problem. And with that, I'll kind of close it up and let the next person take over. Thank you.